we can figure out how many moles we have in things using the ideal gas law, which means we can do stoichiometry. I know you're really excited about that. So in the past, we've done stoichiometry with gas volume, and we've converted it to moles at STP. And how do we do that? We do that using 22.4 liters for every mole. Okay, that has to happen at standard temperature and pressure. So what happens if we're not at STP? Well, we get to add another island, okay, and this is gas, not at STP. And in order to get from moles and back, we are going to use PV equals nRT. Okay, rearrange. That's PV divided by RT is going to equal our moles. And once we find the moles of substance A, we can convert it to the moles of substance B, and then we convert it to anything we want. But what about if we're collecting these moles and then we want to find the volume not at STP of the stuff that we've made or the stuff that we're using? Then we can just add gas, not STP. And again, we're going to use our PV equals nRT formula to get to moles. Okay? So in your workbook, we're going to start out with some class examples. And for you guys, it's on page 106, 107. Okay, and I'm going to start out on 107. 106 is the class examples, but that's the one where we're going to use PV equals nRT. And I want to do this one with you that's at STP, which is just a nice reminder of the stoichiometry we've already done. Okay, how many liters of water? Okay, so question mark, liters over my water. Let's get a little closer for you guys. Okay, is made from 5 liters of oxygen gas and excess hydrogen at STP. That's our key, okay? So we have 5 liters of oxygen gas here as well. Okay, so I'm going from liters of O2 to moles of O2 to moles of H2O to liters of H2O. And just so you can see what that looks like on our mole island, this is what I call mole island plus. I have my gas volume, and then I also have my gas volume not at STP. But we're starting at gas volume at STP, and we're going to a different gas at STP. So gas of our first one, moles to our gas volume. Okay? So let's set that up. So we're going to start with our given, which is 5 liters of oxygen, and I need to do 1, 2, 3 conversions because I went to 1, 2, 3 different islands. Okay, so we start with 5 liters of oxygen. I don't want liters of oxygen. I want to go to moles of oxygen. And for every 1 mole of oxygen, there is 22.4 liters at standard temperature and pressure. Okay, so I'm off liters of oxygen island. I'm on moles of oxygen, but I don't want moles of oxygen. I want moles of H2O. Okay, and it comes from our coefficients from our balanced, I want moles of H2O. This comes from our coefficients from our balanced equation, and H2O, 2, and oxygen is a 1 there. And if you ever forget that your mole-to-mole conversions use coefficients from your balanced equation, it's right there. And then I don't want moles of H2O. I do want H2O, but they want me to find liters of H2O at STP. So for every 1 mole, there is 22.4 liters. Now, it's helpful to see what might cross out before I put in my calculator. I got 22.4 there and 22.4 there. So 5 times 2 is going to be 10 liters of water gas, okay, which is water vapor. So that's a review of how we do our work at standard temperature and pressure. Okay, so now we're going to do these two examples together, and this is part of your work that you have to turn in. So make sure you take a picture of all 3 pages. And now we have how many grams of ACl must be decomposed in order to produce this many liters of chlorine gas, and they give us temperatures and pressures, so we are not at STP. So what do we have to do here? Well, let's look at our mole island. Okay, the first thing to know is that we're going to start with our given, which is 5 liters of oxygen, and I need to do 1, 2, 3 conversions because I went to 1, 2, 3 different islands. Okay, so we start with 5 liters of oxygen. I don't want liters of oxygen. I want to go to moles of oxygen. And for every 1 mole of oxygen, there is 22.4 liters at standard temperature and pressure. Okay, so I'm off liters of oxygen island. I'm on moles of oxygen, but I don't want moles of oxygen. I want moles of H2O. Okay, and it comes from our coefficients from our balanced, I want moles of H2O. This comes from our coefficients from our balanced equation, and H2O, 2, and oxygen is a 1 there. And if you ever forget that your mole-to-mole conversions use coefficients from your balanced equation, it's right there. And then I don't want moles of H2O. I do want H2O, but they want me to find liters of H2O at STP. So for every 1 mole, there's 22.4 liters. Now, it's helpful to see what might cross out before I put in my calculator. I got 22.4 there and 22.4 there. So 5 times 2 is going to be 10 liters of water gas, okay, which is water vapor. So that's a review of how we do our work at standard temperature and pressure. Okay, so now we're going to do these two examples together, and this is part of your work that you have to turn in. So make sure you take a picture of all 3 pages. And now we have how many grams of ACl must be decomposed in order to produce this many liters of chlorine gas, and they give us temperatures and pressures. So our given number, which is 3.1 liters of chlorine, is not at STP. Okay, so our given number, we are going to start at gas volume, not at STP, and we need to use PV equals nRT to get to moles. And then it asks us how many grams must be decomposed. So then once I get moles, I convert it to moles, and then I go right to grams of my thing that I'm trying to find. So we can use our information to solve for moles of chlorine gas, not at STP. Okay, so we have 3.1 liters, that's our volume, and it's at 50 degrees C, which can't stay at 50, okay, and 0.971 atm. So I need to find the moles, okay, 323K. So what do we have over here? We have PV equals nRT, and I'm solving for moles, so PV divided by RT. Okay, so we'll plug in our numbers and we will solve. So here we are all plugged in. I just want to do it in my calculator with you. 0.971 times 3.1 equals divided by 0.0821 equals, and this is also on the bottom, so divided by 323 equals, and we're going to get our moles of chlorine gas is going to equal 0.11, and we have 3 sig figs there. Now, you don't have to round to the end of your answer, but I'm going to just so I don't have a billion numbers for you. 0.114 moles. Okay? So now I have my moles of chlorine gas. So I'm going from moles of chlorine gas to moles of AlCl3 to grams of AlCl3. Okay, so 0.114 moles of Cl2. Okay, but I don't want moles of Cl2. I want moles of AlCl3. Okay, and I have a balanced equation here. So 2 goes with AlCl3 and Cl2, 3 goes with that. Okay, and now I need to figure out how many grams. So I got rid of my moles of Cl2, and now I don't want moles of AlCl3. I want grams of AlCl3. And for every 1 mole, I have to add up aluminum and 3 chlorines. So when I calculated that, I get 133.34 grams per mole of AlCl3, and you put that all in your calculator, multiply, divide, you're going to get 10.133 grams of aluminum chloride, and we only had 3 sig figs, 1, 2, 3. Does the 3 round it? Nope, it does not. Okay, so just to review, our starting information our given was not at STP. So I have to use PV equals nRT to get it to moles. Why? Because it's a gas, and that's our gas formula. And once I'm there, I just convert moles of Cl2 to moles of AlCl3, and then I convert it to grams using the molar mass. Okay? Now, what happens if I start here and I end up not at STP? Well, that's what our next example does. Okay, what volume of nitrogen can be produced by the decomposition of this many grams, and it's not at STP? So I'm starting at this many grams. Okay, now if we have grams, we're starting down here. And right now is where people get lost because they're given 50 grams at all these things, so they think they have to use PV equals nRT here. But remember, that's if you're at volume. If you're given grams, just put it right on your table, and you can see I'm starting at grams. And then what's happening is I am going to convert it, and then our answer wants liters. And why is it not at STP? Because our question says that it is at 25 degrees C and 1.2 atmospheres. So we're going to start with our stoichiometry, and then once we get moles, then we'll use PV equals nRT to convert it. Okay, so I am given 50 grams of ammonium nitrite. Yeah, okay, 50.0 grams of NH4NO2, okay? And then I want to go to moles of NH4NO2, and then I want to go to moles of nitrogen N2. And once I find moles, then I need to use PV equals nRT to find the liters not at STP. Okay, so let's start with that. 50.0 grams of NH4NO2. I don't want grams, I want moles. Okay, for every 1 mole, I'm going to get some grams. I'm going to figure that out later. And I don't want moles of NH4NO2, so I'm going to put it on the bottom. And I'm going to moles of N2. okay? So I have to add up nitrogen, 4 hydrogens, another nitrogen, and 2 oxygens. So my molar mass of ammonium nitrite is 64.06 grams per every 1 mole. And then I needed to convert moles to moles using my mole ratio. And from my balanced equation, ammonium nitrite is a coefficient of 1. And my nitrogen is a coefficient of 1. Okay, so you will get 0.781 moles of nitrogen when you take 50 divided by 64.06 times 1 divided by 1. But that won't do anything. Okay, then we are going to plug it into our PV equals nRT. Why? Because these many moles of nitrogen we're trying to convert to volume of gas, not at STP. So here are my numbers plugged in. My volume equals nRT divided by P. My volume is going to equal 7.81 moles times 0.0821 is your gas constant times 298, your temperature, divided by 1.2. And you can see my moles cancel out, my atmospheres cancel out, my K cancels out. I'm left with liters, and your key's a little off. I got 15.9 liters of N2, and so should you. Okay, so please make sure that you are using your mole island to figure out what you're starting with and where you're going to, because some people see the 50 grams at all these different temperatures and they think they need to use PV equals nRT, but this is mass. Mass does not compress. Gas does. That's why we need to use this formula for gas volume at different temperatures and pressures. Okay?